So we're extremely pleased today to have Binyamini, and he's going to be telling us about O-Minimality and rational numbers.
Okay, thank you very much. So yeah, thanks for the invitation. It's very nice to be here. So the plan for this talk is I will not assume that you know O-Minimality. I'll kind of explain a bit about what O-Minimality is and something called the sharp variant of O-Minimality. And then I'll explain a bit about point counting. And then like my main message will be to try to convince you that this point counting, which is counting rational numbers in O-Minimality, is not just for number theories. Okay, so there are many interesting applications in number theory, and I will kind of not go much into those, and I'll try to give some other applications and convince you that you should be interested, even if you don't work. Okay, so but let me start by just kind of saying what O-Minimality is and what is this sharp version. And I'll define them both at once to save time, but also to show you that the analogy and how it's really kind of almost the same thing. So first, in O-Minimality, we talk about a structure. It's a structure of first order logic. And if you're not familiar with first order logic, then structure S, this is just for me going to be a subset of the power set of R. This joint union power set of R2. Okay, so it's just kind of a collection of subsets of various like defined spaces. And these are called definable sets. Definable sets. Okay, so really we are thinking about the sets that can be defined using like formulas. Formulas in first order logic. But again, I'll give a complete definition. So if you're not familiar with this notion, then it doesn't matter. Now, this is just a structure. When I want it to be sharp, I'm going to introduce some extra information. So basically, a sharp structure is a structure where we want to measure the complexity of these sets in terms of something like the degree. Okay? So it's something like an extension of the notion of a degree to a definable set in a structure. So formally, what I do is I take a filtration omega, depending on two parameters, f and d. So this is a subset of the definable sets for every pair of numbers f and d in N. And now this should be a filtration. So that means that omega fd is contained in omega f plus 1d and also in omega fd plus 1. And so unlike in algebraic geometry, I'm not going to really associate one particular degree to a variety. It's kind of just a filtration. I'm saying I have all the things that are up to format f and degree d. Okay, so it just increases when you increase one of these indices, and you should think of f as, so if the sets are defined by formulas, then this f would be something like the total number of variables in the formula. And the d would be, let's say, the sum of the degrees of all the polynomials in the formula. Okay, so just to set your intuition, but okay, formally I'll just give axioms saying how these things behave. And I want them to cover my entire structure S. Okay, so I want S to be equal to the union over all f and d of this omega f. Okay, so every set has eventually some formatted degree. Okay, and now I'm going to put some axioms. So what are the axioms that make S into a structure or into a sharp structure? So let me start with a pair of subsets of Rn. And now I'll write like, so I write in this side what happens in a structure, and in this side I'll write what happens in a sharp structure. Okay, so a structure should be closed under all the Boolean operations. Okay, so I want, or you know what, even let me do it like this. So, okay. In the structure case, I'm going to just assume that A and B are in my structure. But in the sharp case, I'm going to assume now that A is in this omega f with a certain degree, and B is in omega f with some other degree. Okay, and now I can state the axioms. Okay, so in a regular structure, I want the union and the intersection to be in the structure. Okay, so the structure is closed under taking unions and intersections. And in the sharp case, okay, it should be in the structure, but I also want to say what happens to the format and degree. Okay, so I'm going to say that the union and the intersection belong to omega f and then dA plus dB. You see, so here we're just saying it's closed, and here we're kind of keeping track of how the complexity grows when we take union or intersection. Now I'm going to do that for all the axioms of a structure. Okay, so I want, here I want.
Where does the sharp come from?
What?
Where does the word sharp come from? Complexity?
So at the very end, I'll say that the last axiom, I'll say what it means to be sharp and what other notions one could have instead of sharp. So I want the complement and I want the projection to, let's say, Rn minus 1 to be in my set. Okay, that's like a logical knot. And that's the logical existential quantifier. It's saying there exists like a final coordinate such that the first n minus 1 coordinates are here. And here I'll say the same, but I'll say that the complement and the projection are just in omega fd. So that it doesn't even change the FDA. Yeah, sorry, FDA. Thank you. Okay, and here I want to be able to add a variable. So I want to say that R times A or A times R are in S. And here, I'll say that when you add a variable, you increase the format. So that's in omega F plus 1 dA. And so those are basically the axioms of a structure, any structure of the logic. So you could kind of say that this is the sharp variant of any structure. But okay, for an O-minimal structure, we need a bit more. We need two more axioms. So for the first of them, suppose that I take a polynomial in n variables. Then I want the zero locus of my polynomial to be in S. Okay, so it's kind of an O-minimal structure, what logicians call O-minimal structure over the real field, it always contain all of these algebraic hypersurfaces. And in the sharp case, I would like the same hypersurface to be in omega n deg p. Okay, so it's kind of saying that, okay, we are defining some new notion of format and degree, but it restricts to the old notion, at least on algebraic hypersurfaces. So it's kind of compatible. Okay, and that's still not an O-minimal structure. That's a structure over the real field. O-minimality is a finiteness axiom. Okay, so O-minimal structures are supposed to be structures where everything is finite. Okay, so let me write this final axiom. So now I'm going to take A, which is in R. And then the usual axiom will say that A is a finite union of points and intervals. Okay, so whenever we have a definable set in the real line, it's going to be finite. It's a finite union of points and intervals. And now in the sharp case, I'm going to say more, I'm going to count them. Okay, I'm going to say that the number of these points or intervals is less than or equal to some polynomial, depending on the format, in the degree. Okay, now these polynomials are kind of part of the data that defines the structure. Okay, when I have an O-minimal structure, I have a sequence of polynomials. They depend on the format. Maybe when the format grows, the degrees of this polynomial can grow, but I'm saying that when you kind of fix the format and just increase the degree of the set, this thing grows polynomially, okay, in the degree. And this is kind of where I call it sharp. That's kind of the best control you can expect. Well, unless you want to really understand the degree of the polynomial, but like polynomial growth in degree is unavoidable. That's as sharp as you can get. Sometimes we can't get this. Maybe you can think about other things. Like I sometimes think about effective O-minimal structures where I just ask, well, is there some primitive recursive function, or can you give any effective estimate in terms of a complexity? That's also interesting, but I'll focus mostly on on this case. Any questions so far? Okay, so now what is the point of making a definition like this? So I'll give like one kind of prototypical theorem.
So the kind of theorem about the number of connected components, like,
Exactly.
that's sharp.
Yeah, my next example is a theorem about connected components. So a theorem, which is like a basic theorem of O-Minimality, if A is definable, or in the sharp case, I'll take A in a given format and degree, then the number of connected components is finite, but here it will be the number is less than some polynomial, depending on the format in the degree. Okay, so I mean, even though the axiom was only saying something about subset of the real line, once you use all these other axioms in O-Minimality, you can deduce that any set, no matter which dimension, has finitely many connected components. And if you play the same game, but now in sharp O-Minimality, you can deduce that the number of connected components is actually polynomial. So the idea is that, I mean, kind of anything that you can do in O-Minimality, you can kind of now try to do more sharply and control the dependence on the degrees in this context. Okay, so let me give a few examples.
What was the original motivation for this method?
For the sharp definition or for O-Minimality? For O-Minimality, I think people had the semi-algebraic geometry, and then Rasevich was thinking about the subanalytic geometry, where you include analytic functions, and essentially Gabrielov proved the theorem that was showing the O-Minimality of the globally subanalytic set. So there was a kind of another example that turned out to be O-minimal before this language existed, and then people wanted to kind of see what you can say generally. Well, how can you generalize? And I think the first maybe non-trivial, I mean, the first example of an O-minimal structure that wasn't already known to be O-minimal before the definition is Rx, which is one of the structures I'll mention now. So, okay, what are some examples? So there's R-alg, that's this first case I mentioned, that's semi-algebraic sets. This is kind of take the smallest possible one, right? So don't add any, I said you have to add the polynomials, and then you should close under all of the axioms. And if you just take this, you'll be left with semi-algebraic set. Basically things you can write using formulas, just with addition and multiplication. And this is actually sharply O-minimal, you can see. But perhaps not super surprising, but it's sharply O-minimal because, okay, I mean, we know that for algebraic things, we can associate a degree and I mean, the format in this case would be just a dimension. The next example that people looked at was Rn, which is basically you take R-alg, and then you add to this all of the functions f from 0, 1 to the n to, let's say, to R that are analytic. So analytic means it's analytic in some open neighborhood of this. So it's really analytic up to the boundary.
So when you say you add the function, you mean you add the graph function? Or?
I add the graph and then I close under all of the axioms.
Yeah, that I understand.
Yeah, I add the graph. Yeah, you can say you add the graph. But it's kind of the same as saying I'm going to look at all the logical formulas where now I'm allowed to use these functions. But yeah, I mean, in this definition, definitely, you add the graph of the function to your structure. Okay, so this one are called, I mean, the sets that you get in the structure are called globally subanalytic sets. They were studied by Rasevich and Gabrielov, and it's also an O-minimal structure. This is O-minimal, but it's not sharp. There is no way to associate degree to every analytic function in such a way that these things will work. You can try to see it as an exercise. Basically, if you take a very lacunary function, you will not be able to associate a degree to it. I can show later to anyone who is interested. Okay, so this is again a classic that was kind of known to be O-minimal before O-minimality existed, in some sense. One other structure that I want to mention that is often used in applications is Rnx. And here you basically take Rn, the one I defined here, and you add one unrestricted analytic function. So you basically add this function e to the x viewed as a function from R to R. Okay, so if you restrict this to any compact interval, it would already be here. But if you add the whole thing, it's not here, and it's really a bigger structure. Okay, and this is again O-minimal, and certainly not sharp, because even this one is not sharp. Okay, so the question is, are there some things that are more than R and are sharp? It's not easy to construct even one example. So I'll just mention that there is a structure called restricted Pfaffian. So it contains, for example, the graph of e to the x, sine x, elliptic, or Boolean functions, but all restricted to compacts. Okay, so if I have time at the end, maybe I'll say a bit about this structure and some conjectures about larger structures.
Wait a minute, I'm confused. What, are those functions all analytic?
They're analytic if you restrict them to a compact. They're not analytic at the boundary.
So you're taking, what about sine?
If I'm taking sine x but restricting it to a compact.
Which ones are you restricting? Which?
The substructure of RA.
Yeah, I'm taking all of these functions, for instance, but restricting them to a compact. So all of the functions are restricted. And what I'm saying is,
Substruct behaves better.
yeah, so this is what is called the reduct. So it's all contained in Rn.
Okay.
But these are functions where you can imagine associating a degree. It's not some arbitrary analytic function.
I see. You take some, but you're going to give us an example of this.
And I'm saying that the theorem is that this one, this reduct, is Sharpian. Okay, so kind of you have to restrict yourself from all the analytic things to some nicer analytic things, but then you can construct examples where it is Sharpian. Okay, so there are kind of we don't know much more than this. Maybe you can remove this restriction. If I have time at the end, I'll talk a little bit about what can you do that's bigger than alpha and would still be sharp. But I don't want to get into too many definitions. So just, believe me that there is one structure. It contains various interesting functions, and it does have this nice property of being sharply omnipotent. Now, this structure, for example, it does not contain everything we want. It does not contain, for instance, modular functions restricted to compacts. It does not contain, sections of Gauss-Manin, so period maps. There's various interesting functions that we care about that are not living in this structure. So we do have conjectures, and it would be useful to extend this sharp O-Minimality to larger things, but currently this is.
Can you just say what the properties of the sum differential equation?
So, basically this is defined in terms of functions that have a certain type of differential equation with a triangular structure. And conjecturally, you should have a bigger structure where you don't impose this triangular condition, and it should still be sharply O-Minimal. So if I have time at the end, I'll say a bit more about this definition and the conjectures. Other questions?
Is there any kind of meaningful structure theory of O-minimal, like the set of O-minimal structures?
There is a containment, one inside the other, and we know some things, like there are incompatible ones. So it's not that they are all, one big chain and the union would still be O-minimal. There are two structures where if you took the union of their thing, it wouldn't be. But yeah, I don't know. There are various properties that, an O-minimal structure could satisfy or not satisfy, but I don't know what to say in general.
Are there maximal ones for you?
I'm not sure. I've never thought about it. It's a good question. Okay, so now I want to say a little bit about point counting. Point counting, for me, this word means that we are taking definable sets in some O-minimal structure, and we try to count integers or rationals or algebraic numbers in there. Okay, so let me just make some notation so we can formulate something. So I'll be thinking about subset of Rn, and I'll mostly be talking about this basic case where what we're trying to do is to count the rational points in a set. Okay, so I'm going to denote by this. This is going to be the set of x in x intersect q to the n, such that the height of X is less than or equal to this number H. So the height of a vector like this, if you don't know it, it's a vector of rational numbers, and the height is just take all the numerators and all the denominators and take a maximum. This is the height. Okay, so I mean you can extend this to other number fields, to various other contexts, but this will be enough for my talk. I'll only talk about like this basic case of height. And what I care about is to count the size of these sets. That's what I call point counting. And there's kind of a dichotomy here. If this set is algebraic, then this is a very interesting and very deep problem. I mean, there are very interesting results about when does an algebraic curve, for example, contain infinitely many rationals. That's a different type of story that I want to completely ignore. Okay, so in order to ignore it, let me make a definition. I denote by X alg. This will be the union of all positive dimensional connected semi-algebraic gamma in X. Okay, so it's kind of all the algebraic sets of positive dimension that are in my set. I throw them into this algebraic part. Okay, and then the transcendental part is whatever is left. Right, so the idea is that what you have here is like curves or surfaces that are algebraic, and we're not even going to try. That's a different, it's above our pay grade to try to count rational numbers in this. So we'll focus on the rest where it's all transcendental. And then it turns out that you...
Subtract X out, not X.
Oh, yeah, that would be a problem. Thank you. Yeah, subtract X out. And then, very surprisingly, it turns out that already with this restriction, you can say that. So there's a very nice theorem of Pila and Wilkie. It says the following. So we're going to let X be definable in O-minimal structure. And I'll also fix epsilon a positive number. And the theorem then says that if you count the number of rational points up to height h in the transcendental part, this is always going to be less than or equal to some constant depending on x and epsilon times h to the epsilon. Okay, so as soon as you've removed the algebraic part, in what's left, there's very few rational points. Okay, so this is called geometry governs arithmetic. So I mean, there's some geometric obstruction of having algebraic things in your set. And once you get rid of this geometric obstruction, you can say that there are very few rational points. And this theorem is kind of optimal in the sense that if you look in a structure like Rn, and we know that you cannot really improve it. For any sequence that grows slower than h to the epsilon, for any epsilon, there are actually sets that contain this many rational points. Basically, it's kind of graphs of lacunary functions. And then there was a...
You mean like log?
What?
I mean...
In the sense of log to a power, no?
It's not just that, I mean, it's not just that you can't improve it to log.
Epsilon is shown.
I mean, if you have anything that's slower than h to the epsilon, then already there is a counterexample. You can find a function that will have more. So, I mean, this is really kind of the best that you can hope to do in this generality. Then there was a conjecture that by Wilkie, where if you took sets that are defined in a much more restrictive set using only exponentiation, then you should really be able to improve it a lot. Okay, you should go from h to the epsilon to log h, polynomial in log h. And this sharp O-Minimality definition, it was kind of motivated by trying to do this. So we were trying to find some class of O-minimal structures that are more kind of more controlled and where you can try to improve this asymptotics that you cannot improve in general. So this is what sharp O-Minimality is supposed to do for you. So
Guess the power of law.
So we have not, I'll state some theorems where you do have a bound, but I mean, it has not been worked out, but it's completely, I mean, it depends only on the dimensions, this power of log. So you can, if you like, you can compute it.
Not on the format, on the dimension.
Well, okay, let me not be precise here. It depends on what you mean exactly, but I mean, okay, in some concrete cases, I guess it depends only on the dimension. If you try, I mean, somehow in the general formulation, I always have these polynomials that depend on the format. So it's kind of, if you just use a general formulation, then the degrees that you get will depend on the format. Okay, but so this is the theorem. Let me say what we can do with, I mean, when can we get some better result? So unfortunately, I need one more definition. I promise it's the last one for now. So we cannot quite say, if we just have a sharply O-minimal structure, we don't really know how to do better at the moment, at least. So we need something called a sharp derivative. So I'll say that this structure S, that's sharply O-minimal, has sharp derivatives if whenever I have f, a definable function from R to R, let's say Rn to R, f has format f and degree d, I mean that the graph is contained here, then for any alpha in n to the n, I can compute this derivative f alpha. Okay, wherever it is defined, let's say, I mean, this might not be differentiable everywhere, but let's take this on its domain of definition, and this is going to be in omega. So I'll have some constant depending only on the format, and the degree will be polynomial depending on the format in the original degree and in the size of alpha. Okay, so I'm saying when you take higher and higher derivatives, you don't increase the format. So never mind how many derivatives you took, the format stays the same. And the degree, it grows polynomially in how many derivatives you took. Okay, so this is the kind of thing that you can expect to hold when your structure was generated by solutions of differential equations. Okay, so if kind of this function was, let's say, satisfying a differential equation, algebraic differential equation, when you take more and more derivatives, you'll just get like more and more complicated algebraic expressions in the original function. Okay, and then you can imagine that the degree will grow polynomially. If you just took some, I don't know, gamma function or something where there's no relation between the function and its derivatives, it's much less clear how to get this. So I don't know how to prove that every sharply O-minimal structure has this property. I think probably it's not true. But for structures that are generated by equations, it is true. Okay, so the fact is that this restricted Pfaffian structure does have this, does have this sharp derivative property. Okay, and with this property, we can say something. So let me say what we can say. So this is a theorem by myself, Novikov, and Zach. So under these assumptions, so if we have like this sharp O-minimality plus sharp derivatives, then whenever X is a set of format F and degree D, we have a bound. The number of rational points like H is less than some polynomial, depending only on the format, in the degree and in log A. Okay, so it's kind of realizing this conjecture that we had before, and also it's a bit more explicit. It's telling you, that the polynomial depends only on the format, something like the ambient dimension. It grows polynomially with the degree of the set, and it also grows polynomially with log H. Okay, and this is kind of the best that you can expect again. Even if you are restricting to structures with solutions of differential equations, if you look at something like y is equal to the power x, this is not an algebraic thing, and certainly it contains a logarithmic number of integer points. Whenever x is an integer, y is an integer. Okay, so this is again kind of sharp. And I don't know in which direction one could try to extend this. Okay, so that concludes my quick introduction to O-Minimality and point counting. And now I want to give some examples to convince you that you should be interested in point counting, even if you're not a number theorist. Okay, but I do have to pay homage to the number theory applications. So let me do it as my first example. Unless there are other questions. Okay, so the first example, and that's the kind of example that comes up in applications to number theory, is the following kind of problem. We have some interesting set of points, and we want to count them, and we will translate this problem into counting integers in some other set. Okay, so how does it work? Well, maybe even before I give this example, let me make kind of a general kind of definition that is helpful in thinking about these applications. So why point counting? Why should we be interested in counting integers or rationals? So I want to make a definition that's not really anywhere in the literature. It's just a name that I came up with for this stuff, but it just helps to think about the kinds of applications that you get. So I'll call a set X in R to the N Z tame. If there exists a definable family Z in Rm times Rn, such that X is equal to the union over the integer fibers, alpha in, say, K, Z alpha. Okay, so I'm looking for sets that might not be definable in an O-minima structure.
They are the same or related to one another?
Yeah, sorry, that should be M. Sorry. Yeah, so I think of this set as a family where the first M coordinates are the parameters and the last N coordinates are the ambient space. And now instead of saying that the X is just definable in an O-minima structure, I'm saying you can kind of build it up from all the integer fibers of a definable family. Okay, and kind of the observation
The Z alpha are definable, so it's a union of definable things.
yeah, it's a union of definable thing, but you're only taking, like if you took a union over everything here, then okay, then this X would be just definable, but because you're just taking integers, you are kind of inserting some non-tameness into the picture. So, I mean, tame is another word for definable in O-minima structure. So each of these fibers is very simple. I mean, when you have something definable in O-minima structure, it's very, very simple, and it definitely can't oscillate. Okay, but
X is not in the minimal structure.
X is definitely not, I mean, if it is in the O-minima structure, that would be the simplest case, but it does not need to be in an O-minima structure. So a very simple example is the graph of sine. If you do something like y is equal to sine x, then this is definitely not definable in an O-minima structure. It oscillates. If you intersect with y is equal to 0, you'll get infinitely many isolated points. But it is Z-tame because you can kind of take this, take sine restricted to, you can restrict sine to 0 to 2 pi. This is definable, and then just take the family of all of its translates, right? And then you can glue up the graph of sine from integer translates. Okay, so that's the basic idea, that this kind of allows you to go to some oscillatory things like the sine function and still understand them in some sense using O-minimality. And I claim kind of the observation, which is just it's not a theorem, it's an observation that I've tried to motivate with examples, is that this is a useful notion. So there are a lot of interesting functions that are Z-tame. And when a function is Z-tame, or not a function, a set, many things in math are Z-tame. And when they're Z-tame, you can say something about them because of this point counting. Okay, because I'm only taking integer parameters, I'll be able to kind of count things about my function by counting over the parameter space and applying this Pila-Wilke theorem or this stronger polylog counting. Okay, so now let me give some examples. So in my first examples, I'm going to be thinking about just countable sets that are Z10. I mean, you can apply this to any set X. Let's say that X is just a countable set. You can ask yourself which countable sets are kind of in bijection or in correspondence with integers in a no-minima structure. So, for instance, roots of unity torsion points in abelian varieties. CM points in Shimura varieties, if you know what they are. Are all Z-tame. So let me give kind of the simplest possible example for roots of unity. I could take Z to be, my parameters would be A and B, point would be X, and I want X to be equal to e to the 2 pi I A over B, and I want what? A to be less than B 0, something like this. So this would be a family that's definable and gives me a parameterization of all the roots of unity. Okay, and the important thing to notice here is that I took an exponent and I'm raising, so this is kind of a first order formula where I'm taking the exponent. This is an oscillating exponent. So I cannot write something like e to the 2 pi I times A, because this would not be definable in a no-minima structure. So the important thing is that here I'm taking this E, but I'm only evaluating it where A over B is less than 1. Right, so this is kind of an oscillating function, but I'm actually restricting it to a compact domain. Right, and all of the oscillations are actually hidden in this, the fact that I allow myself to take integers A and B. Okay, so this does give me a Z-tame family where for every pair of integers A and B in the family, I'll get a root of unity X, and every root of unity I'm going to get in this way. Okay, so this is kind of the way that this comes up in number theory. We have some interesting points that we care about. We want to count them. And now let's say I have an algebraic variety and I want to count roots of unity in the algebraic variety. And instead I can kind of lift to this family and I'll say that up to this lift, it's enough to count integers in some other set. Right, and then these point counting theorems from O-Minimality will tell me something about the integers in that set. Okay, so there are many examples where it is used like this. So this is used to prove Mani-Mumford. And also under all in a kind of a method that's called the P-Lasagna method. Okay, so there's a way to approach many problems in number theory by translating them into kind of counting points in some other definable sets strategy. But I want to talk about other examples that are not from number theory. This was mine. This is what I promised. But let me kind of forget about this and go to some other examples.
Then you also need some other ingredients, right? Not just point counting. You need some channel or something.
Yeah, so I'm kind of, whenever you do this kind of thing, there's always some obstruction, right? So in the theorem, Pilo-Wilkie, or also the stronger theorem, you have to remove the algebraic things. So if you analyze a problem in this way, you can translate counting some interesting points to counting integers in another set. And then the question is, does this set that you define contain something algebraic? And there you should somehow figure it out. So there's a very big kind of technology developed for this kind of questions called Axe-Shanwell theorems. And you always need some kind of Axe-Shanwell theorem in order to be able to carry out this strategy. And just for lack of time, I will not say much about the Axe-Shanwell part. But I mean, kind of the strategy is we're going to convert some problems to counting integers in some set. And then hopefully we can rule out having something algebraic in the set. Okay, so I want to show examples where it's not really about number theory, or it doesn't seem to be about number theory. So let me start with a conjecture of Shapiro. So in this conjecture, I'm going to take two exponential sums. I'll take f of t to be sum of aj e to the lambda jt, and similarly with g of t, bj e to the lambda jt. So these are finite sums, just kind of a finite sum of complex exponentials in general. And then the conjecture of Shapiro. So, okay, let me first say that these are z-tame. Okay, e to the z is z-tame. That's basically what I showed you with sine. So, I mean, just the function e to the z is z-tame. And that implies that also f and g are z-tame. You can just kind of glue them up from the z-tame definition. First, e to the t is z-tame, then e to the lambda jt is z-tame, then you can sum them. So this z-tame class is closed under these kinds of operations. And now let me say what is this conjecture, very old conjecture of Shapiro. Yeah, Shapiro. He conjectured that if f and g are coprime, I mean they don't have a mutual divisor in this ring of exponential polynomials, then this set f is equal to g is equal to 0 is finite. And that's probably a very difficult conjecture. I don't know of any, I mean,
If you have, I mean, McIntyre has a paper where he solves it under Chanel.
yeah, it's very difficult, of course. If you know Chanuel, then it's doable if f, for instance, is let's say,
If you assume something like.
so I mean it kind of reduces to Skole-Mahler-Lech, which is also a very interesting theorem in the case that f is just, let's say, a polynomial in one. So if you had, if
These are finite sums?
these are finite sums, yeah.
So this is not just tame, they're definable in our X.
No, but these lambda j's can be complex, so it's only z-tame because you have kind of a sign hiding in there. So it's they are kind of almost periodic fine. They're, you know, if they're all commensurate, then one of these would really be periodic, and then the question is easier. But if you have non-commensurate exponents, then this is not it's an oscillating thing that's not periodic and seems to be very difficult. Now, what this z-tameness business tells us is that we can kind of convert this problem into a problem of counting integers on some set. Okay, so I want to say, okay, let me say what one can prove. So what one can prove using point counting is that, okay, still I'm assuming that f and g are coprime, and that has to do with this assumption of having no algebraic part. And
So who's this? Is it a theorem of yours?
it's a theorem of mine that's not written anywhere. But
That's why I've never seen. Okay.
yeah.
Actually, that's what I haven't seen everything that's.
But let's see what is the theorem first. F equal g equals 0. If you intersect this with a ball of radius r, and this is less than poly log r. So this is based on this.
Coprime. Coprime is that they're not both divisible by the same exponential polynomial.
They don't have an exponential polynomial. I mean, there's a ring of all the exponential polynomials, and there's no one exponential polynomial that divides both of them. If there is an exponential polynomial that divides both of them, each exponential polynomial does have infinitely many zeros. So I mean, you don't need this assumption to have any chance of proving that. And Shapiro says that that's the only kind of reason why you might get infinitely many common zeros. So I'm saying, okay, I can't rule out having infinitely many, but I can show that you will have a polynomial number in log r. Okay, so somehow integers are hiding in this problem, and counting integers is useful for this problem, even though the roots of this exponential polynomial are completely transcendental under Chanuel, and you don't initially expect maybe to use integers for solving it.
But these are complex roots or?
These are, yeah, all the complex roots. Okay, so kind of the way to do this reduction is basically, I mean, suppose that f is z-tame. Z tame. So I can write the graph of X. The graph of X is something like it's contained in the union over alpha of some Z alpha F. Right, and I have similarly the graph of G is contained in the union over some beta of Z beta G. I have these like families that define the graphs of F and G, and then I'll apply counting to basically to the parameters. I want to count now these pairs alpha and beta, such that if I look at the fiber Z F alpha, and so these are kind of two functions now, graphs of two functions, Z G beta share a root. Okay, so now this is going to be some graphs of function. This is going to be graphs of function. I can look at those pairs of parameters for any alpha and beta. This is a definable set now. I'll do it not only for integers. For any alpha and beta, I can write this set. This is a definable condition. It's saying there exists a root. It's a root for both of them. And then in this set, I can try to count all of the integers. And if I know that I have very few integers, that will translate to having very few common roots. And so that's the idea of how it works. And now you should check whether this set can have algebraic parts or not. And here the classical Ax-Shanuel theorem can be used to rule it out. Okay, so that's one example. I want to go to a little bit more exotic example. Unless there are questions.
What is the exact statement that you need? So to just follow this algebraic, what is the exact state sort of about what kind of Ax-Shanuel thing do you need?
I mean, ideally, I would like to say that there are no algebraic parts here, that, I take this set that I defined here and say there's no algebraic part. In fact, it doesn't quite work out like that. There could be algebraic parts, but they all correspond to the same root. So, I mean, you should kind of describe the algebraic part here. It's possible that you are moving in the parameter space, but you're not really moving this intersection point, right? So, I mean, I don't want to give the precise statement, but you can apply Ax-Shanuel, understand exactly how the algebraic part looks here, and then either it creates an abstraction or it doesn't. In this case, it doesn't.
Ax-Shanuel for exponential.
Yeah, this is just Ax-Shanuel for exponentials, yes. Okay, so now I want to give another example that's related to harmonic analysis. Okay, so this is example 3. And okay, so I'll start by kind of saying who is the Z-tame guy here. Now it will be the Bessel function, J1. It's Z-tame. So this Bessel function, again, it's an oscillating function. It's not periodic. It kind of oscillates and decays as you go off to infinity. And I'm claiming that it is Z-tame. And to see that it's Z-tame, you need to know certain formula by Poisson and Jacobi. So the formula is as follows. G1 of x is equal to e to the ix times one function plus e to the minus ix times another function.
There's nothing special about one.
What?
There's nothing special about one. J1?
Yeah, I mean, J for any fixed nu, it's Z-tame. It's a very interesting question if it's Z-tame where you take this to be a parameter. So this is Poisson-Jacobi, the formula I have here. This one. And the important thing about these guys, so these guys are oscillating, right? It's e to the ix. Definitely, they're oscillating, but they're Z-tame. I can glue up this e to the ix from integer fibers. These guys, on the other hand, are not oscillating. So in the classical formula, there are functions that have an asymptotic expansion. But in fact, they are what are called Gevrey functions. So they're both definable in a certain structure called RG. So this is a structure of Gevrey summable functions. Okay, so I will not define it, it will take me a long time. But they're not analytic, they're not in Rnx, but they are definable in some larger O-minima structure constructed by Speisiger and Van den Driest. So because these guys are defined, so they're basically definable, I can just take them as is. These things I can glue up from integer fibers of a definable family, so the whole thing is going to be definable. Yeah, I mean, it's going to be Z-tame in this structure algae. Okay, so why is this useful? I mean, it's an interesting game to look for Z-tame things in general, but I mean, what I want to convince you is that there are kind of natural problems that people have asked before they knew about Z-tameness that you can approach using this. Okay, so let me tell you the conjecture by Fuglede that this relates to. So I'm going to call lambda in R2 an orthogonal set, orthogonal for the disk. If I want here, so I want the integral over d of the 2 pi I lambda 1 minus lambda 2 u du to be 0 for every lambda 1 not equal to lambda 2 in my set. Okay, so basically I'm looking at this e to the 2 pi lambda u, I'm looking at these Fourier characters, and I'm claiming that they are all orthogonal. Okay, so I'll say that this set is an orthogonal set if all the exponentials that I took are orthogonal. Okay, and Fuglede was interested in understanding these orthogonal bases. And what he conjectured, but let me first say why is this connected to Bessel?
Well, you see something.
So I mean, you know, why is it in what is the?
Yeah, it seems like the lambda i's are just real numbers, complex numbers.
No, so I mean, I'm integrating over the I'm integrating. I mean, this disk, think about it as a subset of R2.
Yeah.
So here it's a product. So this U is in R2, and I'm doing an inner product between this.
Okay.
And the connection to Bessel is that the Bessel function is based deep. Okay, so what I'm saying is that kind of this condition that I wrote here about the vanishing integral, it's equivalent to having the J function.
I mean, D is a disk.
D is the disk, yeah, sorry. So this D is just the disk. And I'm saying that this is equivalent to the J function vanishing on all the distances for every R1. Okay, that's it, because J is basically just a Fourier up to some scaling. It's basically just a Fourier transform of the unit disk, the characteristic function of the unit disk. And now what did Fuglede want to know about this? Conjecture by Fuglede from the late 70s, I guess, is that the number of points in any such guy is less than 4. Okay, you cannot have more than 3 exponentials that are orthogonal. Okay, so that's again probably a very difficult conjecture in transcendental number theory. It's kind of telling you something about relations between the roots of the Bessel function. Now we know that the Bessel function has transcendental roots, and that's a result of Ziegler. It's one of the reasons that he invented E functions. But once you take, for instance, 2 Bessel roots, then we know very little about whether they could be algebraically related. So this conjecture seems very difficult to approach. So let me say what we can get about the conjecture. Okay, so to connect it to the kind of thing that we're doing, let me define an algebraic variety. I'm going to take V for 2. So this is going to be the variety of 6 tuples of distances between 4 points in R2. Okay, so I'm taking 4 points in R2, and then I have 6 distances, and I'm claiming that this thing is a proper algebraic well, it's semi-algebraic, but it's contained in a proper algebraic subvariety. Okay, so here this thing is 5-dimensional, and it's 6 tuples, so there's already an algebraic relation that's satisfied. And that's actually why Fouglede had 4 here. So if you took 3 tuples, then you wouldn't get an algebraic relation. 3 tuples, then really, you'll have a 3 tuple of distances and a 3 tuple of numbers, and it's not enough. This thing would be a full dimension. But as soon as you go to 6 tuples of distance between 4 points, you already get some algebraic relation between the distances. And what Fouglede was basically saying, let me just, I want to say that because of this thing, I wanted to introduce some notation. There is a map. Yeah, before I say Fouglede, let me deduce something from that. So the fact is that there exists a definable f from R to R, definable in that structure Rg, mapping integers to Bessel zeros. Okay, again, because the graph of Bessel is z-tame, then I can also intersect it with the points where the Bessel function vanishes, and that's again mapping to integers. Okay, so I have again a map that takes the points I'm interested in, the Bessel zeros, to just integers. And now, what I want to say about Fouglede's conjecture. Sorry.
Oh, this is definable in this funny structure that you.
Yeah, that's definable in Rg. And yeah, so what Fouglede is saying is that there are no points in this V42 have all coordinates that are Bessel zeros. Right, so there's no 4 tuple where all the distances are Bessel zeros. And then using this function, I can say that that's the same as saying no integers in this f minus 1 of V42. Okay, so again, this function is definable. So now this thing is a definable set. And we have translated Fouglede's problem to just saying that there are no integers in this set.
That's usually not something you attack.
Well, I mean,
Get bounds.
showing that there are no integers would be hard.
Yeah.
But let me say what we can do, and I'll end there.
But your notion of Z10 somehow is not here.
I mean, the z-timeless was kind of used for me to get this function. So I'm saying there's a map mapping integers to Bessel zeros. And this map is essentially, you get this map from knowing that the function is z-tame. And once you know that you have this function, you know that basically the problem is counting integers here. And now, of course, we don't know that there are no integers. I think it's probably quite a difficult problem in two-sided number theory. But what we can say, this theorem is now being written by myself, Avner Hiro, Jonathan Pila. Oh, sorry, and also Gadi Kozma. So the number of orthogonal 4 tuples in a ball of radius r is O of R to the epsilon. Okay, so there are very few counterexamples to Fouglede. If you look, you take all these 4 numbers from a ball of radius r, you'll see only R to the epsilon counterexamples.
I was expecting a lot.
Well, I mean, the thing is that this structure Rg, it's kind of a funny structure and it's not sharp yet, or maybe it will not be sharp. But I mean, in fact, I believe that with work we can improve it to log. Once you know this works, you can restrict to compact subdomains and try to control things. And I'm quite sure that this can be improved to log.
For instance, in the Shapiro conjecture, what power of log do you get?
I mean, I have not worked it out. One can check. It's completely.
But it's not going to be 2 or 3.
If you told me I really want 2 and I try to push it as low as possible, then I'll see what I can get, but it's hard to say. So sometimes this power can be quite delicate. So if you got, for example, a very good power in Wilkes conjecture, just for this parallel counting, this would prove the 4 exponentials conjecture. So there's a way to deduce conjecture transcendental number theory from this Wilkes conjecture, but I mean exactly how many independent exponents you can get depends on this power. So I mean I have tried quite a lot to push this further, and I know that Jonathan tried. It can be a very delicate issue. The question is, how good do you need the exponent to be? Okay, I have other examples involving orthogonal polynomials, but I'm out of time. But kind of the general message is that whenever you have these kinds of, for example, asymptotic expansions, as I have here. So these asymptotic expansions are very prevalent. They come up in the saddle point method. So for many problems in physics, when you evaluate orthogonal polynomials, when you evaluate eigenfunctions of Laplacians, in all kinds of places, you can get these kind of asymptotic expansions for functions. And whenever that happens, it's quite plausible that your function is Z-tame, and then you might be able to say interesting things about its geometry using this theory. Okay, I'll finish here. Thank you very much.
There's old conjecture, I think, by genre about spherical harmonics in 0 sets. I remember Bergen was very interested in, maybe Rudnick also.
Yeah, so I mean,
Do you have bounds for that?
my last example that I will not write, but I'll say. So there's a question that goes back to Stiltius in a letter to Hermit. It's about Legendre polynomials. So you take Legendre polynomials, it's just a sequence, a very nice sequence of polynomials considered by Gauss and Legendre. And the question is, can these Legendre polynomials have common zeros? Like, can Pn and Pm vanish at the same point, except the origin? I mean, the origin is special, and it's open. And a lot of this thing applies here as well. You have these asymptotic expansions for Legendre orthogonal polynomials, and what we can show in progress is that Pn and Pm can have like a power of log. So the maximum number of common zeros is like some power of log.
Was anything done before? Is this better than what was done before? Were there no results?
I don't know that anything is known. It's some special cases around. So if you take like P sub n where n is prime, then it's known to be reducible, and then it can share. So some cases are known, but it's not known to be reducible in general. And in fact, I mean, we have a kind of program for doing a Money-Mumford type problem for these Legendre or other orthogonal polynomials. And we really weaken. So it means that now you don't need to know that they're irreducible. You just need to know a Galois bound, like that. They don't have roots of very small degree. But I don't know that anything further is known. So far, it's similar to my other problems where there's a very hard conjecture, and we are able to show that there are kind of very few counterexamples. We're not quite proving the conjecture.
More speed with fidelity, more coming.
Then you have a Galois action, which is, yeah.
You're up there.
Because then you would be able to, from some bound, be able to define it.
Yeah, so I mean, with Legendre, we're not able to do it, but with Hermit and Laguerre polynomials, for example, that are known to be reducible, we are actually able to prove a full Money-Mumford type statement in any dimension because you have a Galois lower bound. But for Legendre, there is no Galois lower bound. Yeah, I'm happy to discuss.
I can turn it off. If the beeping doesn't stop within like
Mark?
2 minutes.
For this theorem, you have to eliminate an algebraic subset, right? So just briefly, what goes into that?
So that really depends on the example. So in my first example with Shapiro, everything is defined using exponents, and it's really the classical Ax channel. When I did it here with the Bessel function, for instance, a big part of that paper was proving Ax channel for the Bessel function. Okay, so we use differential Galois theory to kind of describe when you can have. And essentially what we prove, we are not proving only for this V42, we are saying what are the special subvarieties, it's only basically diagonals. Then the claim is in any variety, if you look for these coordinates where they're all Bessel zeros, the only thing that you can get is diagonal. And of course, if you took x is equal to y, then whenever x is a Bessel zero, y is a Bessel zero, and that's essentially all you can get with Bessel. Then when we do it for orthogonal polynomials, you need another Ax-Channel theorem for orthogonal polynomials. So I kind of hid under the rug a lot of the difficult work. But let's say if you come up with a situation where this seems to apply, then, I mean, then you've already made a big step. Now you can try to analyze Ax-Channel. There's a lot of like technical tools for trying to prove these Ax-Channel theorems. So I mean, usually in my experience, if you have come up with some setup where this counting seems to work, then you will be able to do the functional transcendence in many cases.
Let's thank our speaker.